Welcome to Unit 2, Lesson 25, titled Solving Problems with Systems of Linear Inequalities in Two Variables. In this lesson, we're going to focus on using systems of inequalities to solve problems. We only have one learning target today. You should be able to explain how to tell if a point on the boundary of the graph of the solutions to a system of inequalities is a solution or not. Our warm-up today is 25.1, titled Which One Doesn't Belong? Graphs of Solutions. On these, they want you to come up with an excuse as to why each of these graphs is the one that does not belong. For example, A is the only graph that is graphing a system of equations rather than inequalities. When we graph equations, we get a line. When we graph inequalities, we get a line that is either solid or dashed, and we get shaded regions. So A is the only one that is graphing equations. B is the only one that is graphing parallel inequalities. These inequalities are never going to cross. Therefore, they are never going to have a solution. One inequalities solution set is in the light blue, the others is in the lined shading, and those are never going to overlap. C is the only one that has a solution to a system of inequalities. And D is the only one that is not graphing a system. It is graphing a single inequality. So here you can see the differences between graphing equations or graphing inequalities. You can see what it looks like to have a solution to a system or not having a solution to a system. And you can see what it looks like when you're graphing a single inequality versus graphing a system of inequalities. Our next activity is 25.2, titled Focusing on the Details. Here are the graphs of the inequalities in this system. So we have x is less than y, which is represented by the blue shading and the dashed line that creates it. Then we have y is greater than or equal to negative 2x minus 6. And that is represented by the line shading and the solid line that creates it. They want us to decide whether each point is a solution to the system. Be prepared to explain how you know. So the first point is at 3, negative 5. That means x is 3 and y is negative 5. That point is right here. That point is only in the solution region for the bottom. So no only solves bottom. Our next point is 0, 5. That means x equals 0, y equals 5, and we're right here on the y-axis. This point is in the blue shaded region and the line shaded region. So it is a solution. The next point is -6, +6. That means x is -6, y is +6, and that point is right here on the solid line that creates the double shaded area. So that is a solution. Next point is 3, 3. That means our x value is 3 and our y value is 3, and we're right here on the dashed line. Now, even though this part of a line is creating the double shaded area, dashed lines are never solutions. And lastly, we have -2, -2. And this might be the most confusing point to you. It is right here where the lines cross at the corner of the double shaded area. But remember, dashed lines are never solutions. So even though the lines are crossing right there, it's only solving one of them and not the other. For the points on the lines, how did you determine if they were or were not solutions to the system? They must be on a solid line that creates the double shaded area. If they're on the solid line that doesn't create that double shaded area, they're not solutions. If they're on a dashed line, it doesn't matter where they are, dashed lines are never solutions. So we want solid line that creates the double shaded area. Our next activity is 25.3, titled Info Gap, Terms of A Team. So on this one, we are going to have a card sort. On our card sort, we have problem cards and data cards. And we want to use the data card to answer the questions for that corresponding problem card. And what we're looking for is how do these data points allow us to understand the questions? Number one, a team has 6 adults and 8 children. does the team meet all the membership rules of the competition? So we look through the rules. Number one, a team without adults is allowed. Well, that doesn't apply because this team has 8 children. Number two, a team with only adults is not allowed. Well, that doesn't apply. Again, we have 8 children. If 3 adults are on a team, this does have 3 adults, there must be at least 6 children. And there are, we have 8. So we're still good. Number 4, each team must have no more than 16 members in total. 6 plus 8 is 14. Therefore, we do not have more than 16 members, so we're still good to this point. The last rule says the number of adults must be at most half the number of children on the team. So if we have 8 children, then half of 8 is 4, and this team has 6. Since they have more than half the number of children, they would not be eligible for this competition. Question number 2, what is the maximum number of adults allowed on a team? So we know we can't go more than 16 members total. So if we start out with 3 adults, there must be at least 6 children. 3 plus 6 is 9. We're still good. If we have 4 adults, then there would need to be twice as many children. So 4 plus 8 is 12, and we're still under the 16-person limit. So there could be 4 adults. If we have 5 adults, twice as many children would be 10. 5 plus 10 is 15. We're still under the 16-person minimum, so we could have 5 adults. Now if we try to go to 6 adults, twice 6 is 12, so there would need to be 12 children, and 6 adults plus 12 children would be 18 members, which is more than the 16-member limit, so we could not have 6 adults. 5 adults is the maximum number of adults that we could have on the team. Now we can look at problem card 2. We have a new set of rules given to us by the 4 rules and this graph. Question 1 wants to know, what is the minimum number of members that a team could have? How many adults and children would be on that team? So now we need to look at data card 2. A team with only adults is not allowed. So we must have children on the team. A team with only children is not allowed. So we must have a mixture of children and adults. The number of children must be at least 3 times that of adults. So for every 1 adult, there must be at least 3 children. And the total number of people cannot exceed 20. Now if we look at the graph represents a rule about the number of adults on a team. And we see that our blue shaded region is bordered by a solid line where adults equal 2. So that is telling us there is a minimum of 2 adults on the team. And if the number of children must be at least 3 times that of adults, 2 times 3 is 6. So the minimum number of members that a team could have is 2 adults, 6 children, for a total of 8 people on the team. And our last question, what is the maximum number of adults allowed on a team? So what we can do is start with 2 adults, multiply by 3 and get 6 children. 2 plus 6 is 8. That is below the maximum of 20. So we could have 2 adults. 3 adults times 3 children would be 9 children. 3 adults plus 9 children would be 12. We are still not exceeding 20. So we could have 3 adults. Now we try 4 adults. 4 adults times 3 would mean 12 children. 4 adults plus 12 children is 16 total people. We've not exceeded 20, so we could have 4 adults. 5 adults times 3 would mean 15 children. 5 adults plus 15 children is exactly 20 people on the team. We cannot go any higher than that, so the maximum number of adults on the team would be 5 adults, because then we would have 15 children and a total of 20 people. So 5 adults is the answer. So which membership rule does each shaded region on the graphs represent? In situation 1, the blue shaded region tells us as the number of adults increases, so does the number of children. The lined shaded area tells us we have 16 adults and no children, or 16 children and no adults. So the line shaded region is the total number that could be on there. So our solution would need to be in this double shaded area. In situation 2, this solid line and the line shading below it represents the maximum of 20 people and all the combinations that could hit that. The blue shaded area and the solid line that creates it are the number of adults that you could have, meaning you can't have less than 2 adults on the team. And this solid line and the close together line shading is telling us for every adult we have to add 3 children. So the possible combinations of team members must be in this middle triangle area that is triple shaded with both line shadings and the blue shading and the solid lines that create that triangle. Can all the clues be written as an inequality? If so, what are they? They can be. If we look at our first clue is that a team without adults is allowed. So that could be adults is greater than or equal to 0. A team with only adults is not allowed. So that could be children are greater than or equal to 1. If 3 adults are on a team, there must be at least 6 children. So that could say 3A is less than or equal to 6C. Each team must have no more than 16 members total. A plus C is less than or equal to 16. The number of adults must be at most half the number of children on the team. So 2A is less than or equal to C. Now, if we look at the second situation, A team with only adults is not allowed. C must be greater than or equal to 1. Must be at least one child. A team with only children is not allowed. A must be greater than or equal to 1. The number of children must be at least 3 times that of adults. So 3A must be less than or equal to C. The total number of people cannot exceed 20. A plus C must be less than or equal to 20. And then using the graph, we see that A must be greater than or equal to 2. So all of the rules on both data cards could be written as inequalities. Should we graph them all? Why or why not? If you already have it graphed, such as A must be greater than or equal to 0, or C must be greater than or equal to 0, those are our x and y intercepts. You wouldn't need to graph those. Here, where we had a rule that said there must be at least one adult, but we had another rule showing there must be at least 2 adults, you could graph that if you want, but it's not necessary. How does the first set of graphs help us answer questions about whether 6 adults and 8 children are acceptable? So if we look at 6 adults and 8 children, that point is right here. So while that point does solve one of the inequalities, it doesn't fall within our double shaded area, so it does not solve both of them. How do they tell us about the maximum allowable number of adults on a team? So here we know that the maximum number of adults must stay below this solid line because that's the total number of people that we could have. It also has to stay below this solid line because the number of children can only be twice as much as the number of adults. So we know that the maximum number of adults must be below these 2 solid lines or on those 2 solid lines. How does the second set of graphs help us find the minimum number of team members and the composition of the team? Well, for the minimum, it's going to need to be below this solid line or on it. It's going to need to be below this solid line or on it. And it's also going to need to be at least on this solid line. So now we know that the minimum composition is going to be on this portion of the solid line. And total, it could be anywhere on these 3 pieces of solid line or in the triple shaded region. Our lesson synthesis: solving problems with systems of linear inequalities in 2 variables. In the graphs of the first system are points on the 2 lines, such as 14,2 or 8,4 solutions to the system. How do you know? So I would go to 14 for my x and 2 for my y, and it is on the solid line that creates the double shading. So it is a solution. 8, 4 means I go over to 8, up to 4, and I can see that I am on the solid line that makes this side of the double shaded region. So it is also a solution to the system. Solutions are in the double shaded area or on the parts of the solid lines that create that double shaded area. In this situation, are points on the horizontal axis solutions to the system? So we looked at the rules, and the rule said a team without adults is allowed. And the horizontal axis is 0 adults. So since that is allowed, then this portion of the double shaded region is a solid line for the axis. Since it's a solid line that creates the double shaded region, that would also be a solution to the system. In the graphs of the second system are points on the boundaries of the overlapping triangular region solutions to the system. Because I have a solid line here, a solid line here, and a solid line here, then yes, all three boundaries are solutions to the system. My solutions can be in the triple shaded area and on the portions of solid lines that create the triple shaded area. Our cooldown today is 25.4, titled Widgets and Zerls. This is available on the Kidam website. A factory produces widgets and zerls. The combined number of widgets and zerls made each day cannot be more than 12. The maximum number of widgets that the factory can produce in a day is 4. Let X be the number of widgets and Y the number of zerls. Select all the inequalities that represent this situation. So widgets are X and zerls are Y. And the combined number cannot be more than 12. So that would be X plus Y. It could be less than 12. It could be exactly 12, but it cannot be more than 12. Then the maximum number of widgets, so maximum number of widgets is 4. Widgets is X, so X can be less than 4. It can be exactly 4. It just can't be more than 4. So B and D are solutions to this one. Here are graphs of X equals 4 and Y, or X plus Y equals 12. Complete the graphs by shading regions and adjusting line types as needed to show all the allowable numbers of widgets and zerls that the factory can produce in one day. So we said X plus Y needed to be less than or equal to 12. So because it's or equal to, We are going to keep the solid line, and we're going to shade everything below it. This is combinations of x and y that will be less than 12. The solid line is combinations of x and y that will equal 12. Our next one was x is less than or equal to 4. Because it's or equal, we're going to keep the solid blue line. And because we want less than, we're going to shade everything to the left of the solid blue line. So everything in the shaded blue region makes it true because it's less than 4. Everything on the solid blue line makes it true because it's equal to 4. So now our solution area is going to be the solid lines creating the double shaded area and everything in the double shaded area. Everything in the double shaded area makes this less than 12 and less than 4, and everything on the solid purple line makes this equal 12 or equal 4. So now they want us to check 4, 5. That means I go over to 4, up to 5, and I'm on the solid purple line, creating the purple shaded area. So that is a solution. Then we look at 11, 1. I go over 11 and up 1. I'm on the solid black line, but this only makes x plus y equal 12. It does not make x equal or less than 4. So this is not a solution. Then we have 4, 12. We go over 4, up 12, and we're on the solid blue line. This does solve x is less than or equal to 4, but it does not solve x plus y is less than or equal to 12. So it is not a solution. And then we have 3, 9. I go over 3, up to 9, and I am on the solid purple line, creating the double shaded area. So this does make x less than 4, and it does make x plus y equal 12. So it is a solution to the system. Again, our solutions are any points in the double shaded area or on solid lines creating the double shaded area. We have 2 glossary terms. Solutions to a system of inequalities. All pairs of values that make the inequalities in a system true are solutions to the system. The solutions to a system of inequalities can be represented by the points in the region where the graphs of the 2 inequalities overlap. System of inequalities. 2 or more inequalities that represent the constraints in the same situation form a system of inequalities. Our one learning target for this lesson is that you should be able to explain how to tell if a point on the boundary of the graph of the solutions to a system of inequalities is a solution or not. If you understand how to do that, then you are on track for our test on Thursday, November 30th. If you're not quite sure, make sure you ask me questions before the test day.